Hi, in this first video we're just going to take a quick recap over charge, current and time. In this video we've got this circuit set up here with a cell with 1.5 volts, our ammeter, we've got a lamp and just a closed switch. So one thing to be mindful of when working with circuit diagrams is that there is a positive terminal and negative terminal. The longer of the two lines represents the positive end, the shorter represents the negative end. When we're drawing these circuit diagrams, the convention is that flow goes from the positive end to the negative end, like that. That's based on kind of old knowledge really, and it's not actually correct, even though that is the way that we still draw them. So what we know about electrons is that they have a negative charge, and two things with the same charge actually repel each other. So actually what happens is electrons are repelled from the negative end, and they actually flow from the negative to the positive end. That's something you need to know. So electrons are repelled from the negative end, move to the positive end, but I'll just get rid of that. But when we're drawing circuit diagrams, we actually draw them kind of from left going round to right. That's just how it's always been done, and that's based on before it was discovered about electrons moving that way. So for this video, we're just going to think back to the work we did on atomic structure when we looked at metals and how you had these positive cations, or just cations, that had donated all of their electrons to the sea of electrons, and they had no fixed position. They were delocalized, which meant they could kind of move around everywhere. In a wire, this means that they can flow freely. So what we're saying is we've got negative electrons that can now flow freely around a wire. And if we think back to what charge was, well, charge is just these negative electrons. They're negatively charged, and it was a specific number. It was 6 billion electrons of negative charge. Well, to work with that number becomes quite unruly, so we just say we can measure it in coulombs. So we'll say that 6 billion electrons is equal to 1 coulomb. So 6 billion of these equals 1 coulomb. It's just an easier number for us to use. So that is the unit of measurement that we use, but when we're writing equations, it's a capital Q that we use. So capital C when we're writing down units of measurement, capital Q when we're using it in equations, which we'll come to in a short while. And then current was just the flow of this charge. So it's how many coulombs flow every second. So it's basically the flow of 6 billion electrons that flow every second equals the current. So rather than saying we've got 6 billion electrons flowing every second, we can just say that we've got 1 coulomb per second, and to make it even easier than that, we can just say that's 1 ampere, or amp. So 1 amp equals 1 coulomb of charge per second. So 1 amp equals the flow of 1 billion electrons per second. But you know, it's a little bit easy to say 1 amp equals 1 coulomb per second. And remember that these charge and current are linked together, and they're linked with time as well. So we can use this formula here. So overall charge equals current times the time. So if we want to work out the overall number of electrons or number of coulombs that have flowed through a circuit, we need to multiply the current, so the number of amps, by the time taken. So however many amps and how long it flowed for. So if we had added our circuit over here, we had a current of 2 amps and there was a flow for 5 seconds. We could bring that down to our equation, and we could remember the layout that we're using for this. So Q equals current, which is 2 amps, multiplied by the seconds, which is 5, so Q equals 10C. And remember that we can convert this formula into a formula triangle, which is going to help us. So wherever you see two things that are like multiplied together, you just find the thing that you're trying to find out and you kind of whip it up here, and that becomes a triangle. So we'll just do that a little bit more neatly here. So Q at the top, current times time. So this here is your dividing line. In the middle here is multiply. So remember that if we want to figure something out, we cover up the thing that we want to find out. In this case, if we want to find out t, it would be t equals q divided by I. So if we wanted to find out the time, we'd have to take the total charge and divide that by the current. If we wanted to find out the time, beg your pardon, if you want to find out the current, well, pause the tape a second and just see if you can figure that out. Yep, so we just cover up the current with our thumb, and that leaves us with I equals Q over T. So the current would be the total charge and the time that it was flowing for. So if we come back to this example here, the ammeter is reading 3 amps, and in this example, let's pretend that there is 6 coulombs of charge that's being transferred. So we need to figure out the time. So time equals Q for charge divided by current. So that's T equals 6 coulombs divided by 3 amps. So T would equal 2. So that tells it's 2 seconds. The important thing to remember is time is always measured in seconds. So wherever you get a question that asks you about minutes, remember that you need to multiply by 60 to get the number of seconds. So if you're asked about the time that flowed in 7 minutes, we need to do 7 times 60, which would just be 420 seconds. 420 seconds, which would then give you the correct answer. Well done.